Buenos dias, muchachos. Okay, late start Monday, May 18th, 2020. Today, we're here to learn how acidity is measured. So, you guys know that the pH scale is used to measure acidity. And you might remember that things with a low pH, less than 7, are considered acidic, and things with a pH of 7 are considered neutral. And things that have a pH that's greater than 7 are considered basic, which is the opposite of acidic. So we're here to start to understand why that is. So how acidity is measured. So before we do that, let's just review what we did last time, which was the auto-ionization of water, which is water dancing with itself. So in that case, we have two water molecules, and one water molecule steals a proton from another water molecule. And a proton's the same as a hydrogen ion, so the 3 indicates one more hydrogen, and the plus indicates that it's not the whole hydrogen atom that it got, it's just the proton from it. And then the other one's left with missing a proton, so it's a hydroxide ion. So fine, we did that last time, and review that video, please, if you didn't understand what I was talking about just there. Okay, so here it says that the concentration of those hydronium ions in a solution determines the acidity of a solution. So I wrote this two different ways. I said concentration of hydronium, and then I put the symbol or the model for hydronium in square brackets. Whenever you see the square brackets like that, it means you're talking about the concentration of whatever chemical it is inside of the brackets. And they're usually talking about units of molar concentration or moles per liter. So if you know how many moles per liter of hydronium you have, then you know how acidic your solution is. That's what I'm talking about. Okay, so we're going to look at 3 different solutions. The first solution we're going to look at is going to be pure water. And I didn't model water molecules in here because there's so many of them that we wouldn't be able to see what we're looking at here. What we're looking at here is hydronium ions and hydroxide ions. And I'll use red or the orange to keep track of hydronium ions. So if we count how many hydronium ions we have in here, it looks like we're modeling 3. And if we count how many hydroxide ions we have in here, it looks like we have 3. Yeah? So our concentration of hydronium is the same as our concentration of hydroxide. I'm showing them on a balance here. They're balanced. They're even. So hydronium ion concentration, that's what that says right there, is equal to hydroxide ion concentration. So another way to say this right here is that the hydronium ion concentration is the same as the hydroxide ion concentration. If that's the case, and you stick a pH probe into your solution. A pH probe is an electronic device that tells you what the pH is. Back in the day, they used to use paper that reacted with the solution and turned different colors, but that's kind of become obsolete with these electronic probes right here. So if our electronic probe says that the pH is equal to 7.0, the reason it's going to say that is if and only if the hydronium ion concentration is equal to the hydroxide ion concentration. And if the pH is 7, we can quantify, that means put a number to the concentration of hydronium, and the concentration would be 10 to the negative 7th molar. That's 0.0000001 molar. Yeah? Way less than 1 molar. 7 orders of magnitude less than 1 molar. So it's a really small concentration, 1/10 millionth molar. Yeah, fine then. That's what pure water is like. Let's look at an acidic solution this time. In an acidic solution, let's see, we've got 1, 2, 3, 4 hydronium ions, and we have 2 hydroxide ions. So we have more hydronium than hydroxide. So what I'm going to do is I'm going to show we have lots of hydronium by making the concentration of hydronium really big. And I'm going to show that we have a little bit of hydroxide by showing that it's small. So if you put these on a balance, the amount of hydronium would far exceed the amount of hydroxide. And that's what would make this solution acidic. What makes a solution acidic is when your hydronium ion concentration is greater than your hydroxide ion concentration. Yes? And if we measured the pH of this, let's just say it's an acidic solution. So the pH is going to need to be less than 7. So I'm just going to make up a number here. I'm going to say 3.0. These quantities, I'm just modeling this just for illustrative purposes. This is not to scale. Something with a pH of 3 is not going to have actually 4 hydroniums and 2 hydroxides. I just made that up. But it is going to have more hydronium than hydroxide, more hydronium than hydroxide, more hydronium than hydroxide. And if the pH is 3, it is true that the hydronium ion concentration is going to be equal to 10 to the negative third molar. This is true. If the pH is 3.0, then the hydronium ion concentration is 10 to the negative third molar. And I'll show you how that works with the calculator next time. I'm going to come back to this and we're going to bust out the calculator and we're going to figure out how you go from pH to hydronium ion concentration and from hydronium ion concentration to pH. That's what we're doing next time. So that's an acidic solution. Yeah. For a basic solution, let's see what we got. In our model here, we got 1, 2 hydronium ions, and we've got 1, 2, 3, 4 hydroxide ions. So what that means is that we have a relatively small amount of hydronium and a relatively large amount of hydroxide. We got more hydroxide, so it's weighing down this scale. We got more hydroxide than hydronium. This is a basic solution. In a basic solution, the amount of hydroxide is greater than the amount of hydronium. And the pH needs to be greater than 7 if it's going to be a basic solution. So if it's a basic solution, my pH needs to be greater than 7. So maybe I'll just make up a pH of 10, let's say. Yeah? So if your pH is 10, then your hydronium ion concentration is going to be less than 10 to the negative third. In fact, it's even going to be less than 10 to the negative 7th. It's going to be, in fact, can you guess? Can you guess? That's right. The hydronium ion concentration is going to equal 10 to the negative 10 molar. And yes, this number is bigger than this number in magnitude, but it's a negative number. So if you look at it like on the number scale, it's a Am I going the right way? Is that left to you guys? Is that right? Left? I don't know. Can't really figure that one out. But anyway, it's going to be less than 0, more or less than 0. 10 to the negative 7 is more or less than 0 than 10 to the negative 3. Yeah? So this number is smaller than this number. Do you guys believe me that this number is smaller than this number? I hope you do, because if you can believe that, then you can believe that the hydronium ion concentration is lower. And acidity is a measure of the concentration of hydronium. So the bigger this number is, the more acidic it is. And the smaller this number is, then the less acidic it is. But it's the opposite with the pH scale. With the pH scale, the smaller this number is, the more acidic it is. And the bigger this number is, the less acidic it is. And that's because the hydronium ion concentration of something with a pH of 7 is 10 to the negative 7. And 10 to the negative 7 is smaller than 10 to the negative 3. You have to believe that in order for this to work. You have to believe that 10 to the negative 3 is a bigger number than 10 to the negative 7. So that is how acidity is measured. It's measured with pH probes, and pH probes measure the concentration of hydronium ions. Okay, that was good. I think we did pretty good on that one, you guys. So I'll see you guys tomorrow. And tomorrow we're going to do some calculator work, and it's going to be sweet. Okay, peace out.